This episode is all about Huffman decoding. If you didn't catch the one on encoding, you should probably check that out first because it directly follows from this one. Okay, so now we have this bit string without the benefit of spaces to separate the symbols. So how's this work? We break out our Huffman tree, the same thing that we used to encode the data in the first place, and we're going to use that. So we start by placing a cursor at the root of the tree, and then we're going to read a bit one item at a time. So when we see a 0, we're going to update the cursor for the tree to point to its left child. And if we see a 1, we're going to point it to the right child. So when the cursor ends up at a leaf node, we're going to stop. We've reached the encoded data, and we're going to output whatever symbol is there. We'll reset the cursor back to the root of the tree, and then we're going to continue doing that until we run out of bits. Okay. So starting from the root, the first character we see is a 0. So we're going to follow the left child. That's not a leaf node, so we're just going to read the next bit, which is a 1. So we're going to go right. Also not a leaf. Read a 0. We're going to go left, which is still an internal node. It's not a leaf. We read a 1, so we go right. And now we actually do encounter a leaf node. So we emit the symbol that's at that node, which is a T. And then we reset the pointer to point back at the root node of the tree, and we're going to keep going. Okay, so the next bit is a 1, go right. 0, go left. 1, go right. 0, go left. Okay, now we found a leaf node for H, so we're going to emit that. So this process continues for a while, and eventually we decode the message, which was the health of an ox. Honestly, I don't know why I picked that string. It was just the first thing that came to mind that could be encoded with the corpus that we started with. Anyway, so now you know how to make your own Huffman codec. This coding scheme is a way to losslessly encode and compress information. Along the way, you made heavy use of a priority queue, a binary tree, a binary heap, and a lookup table. The priority queue itself is probably best built using a min binary heap. There's loads of compression schemes, but if you implement one like this, you probably are better suited to appreciate the other ones.